Hello, my name is Peter Wonka, and I will present an overview of the Visual Computing Center at KAUST, also called VCC. The VCC currently has 9 faculty members who publish academic research in the areas of computer vision, computer graphics, visualization, and machine learning. Altogether, the VCC has about 150 people, including faculty, research scientists, postdocs, students, interns, and staff. The VCC is well embedded in the international research community, and our researchers collaborate with other great universities, industrial partners, and the government. We strive for academic excellence, as evidenced by high rankings from websites, such as CS rankings, that track publications in the best conferences in different subject areas. After leaving the VCC, our alumni find employment in other prestigious universities as faculty or postdocs, or in leading companies or startups in the field. The VCC is organized according to the Visual Computing Pipeline. The center has research groups whose experience together cover all stages of the pipeline. I will now quickly walk you through the pipeline to give you an impression of the research we are doing in the center. In the computational imaging stage, we consider various forms of data, such as single images, videos, laser scans, industrial tomography, or cryo-EM. After acquisition, visual data is being processed to complete tasks such as object recognition, segmentation, action recognition, and 3D reconstruction. New designs can be generated based on acquired data or even starting from scratch. Example projects in our center deal with architectural designs, CNC machining, modeling of molecular structures, or editing of photographs and videos. Simulation is used to breathe life into geometric data in complex designs, and to evaluate them within different environments. For example, we can analyze the implications of climate change on different urban design proposals and specify strategies to mitigate the impact of natural disasters. Visualization is used to present large-scale datasets from previous stages, such as weather simulation data, molecular structures, brain scans, or geological data from the oil industry. Based on the experience gained in applied projects, our faculty also contribute to theoretical foundations in geometry, optimization, numerical simulation, and machine learning. These theoretical foundations are useful to inform the next generation of algorithm development. Next, we will show selected research highlights.
One of the themes of the VCC is the development of visual computing techniques for scientific imaging. At the core of these efforts has been a sequence of works on space-time reconstructions for imaging modalities like computed tomography. Those normally degrade rapidly in the presence of moving or deforming objects. Our work is based on developing new regularizers for inverse problems. These are inspired by continuum mechanics. This framework has been applied to a range of scenarios from composite material analysis to combustion research, for example, monitoring soot plumes or fuel injection processes. The addition of physics-based priors to the same framework allows for adoption to these techniques to single-camera fluid imaging. In recent work, we adapt this work to holographic particle imaging, as you can see here. We also target other multi-image acquisition modalities. In the future, we intend to increasingly adopt neural representations for reconstruction tasks. We have promising initial results on still tomography and are planning further work on space-time reconstruction with joint learned and model-based priors. Similar space-time tomography methods have also been used for tilt series electron microscopy, in particular of the SARS-CoV-2 virion. You will hear more about this data from my colleague Ivan.
Welcome to the Nano Visualization Group at the Visual Computing Center. In our group, we perform research in visual computing technologies that make it possible to extract, model, and represent nanoscale details of biomolecules, viruses, and cells and their organelles. Typically, we would start with cryo-electron tomography reconstructed using methods presented by my colleague Wolfgang. Such data can be directly visualized using novel rendering techniques that exploit deep learning to automatically separate the specimen details from the background and show the data in a clear way. By matching atomistic building blocks to this data, we can generate models at the nano level of detail. The model generation relies on data and associated procedural rules that govern the model synthesis. Such models can be used to communicate how a virus looks like in augmented reality, for example. Clip. Done. In the future, these models can serve as a starting point for a live simulation on nanoscale. You will hear more about simulation from my colleague Dominik.
Climate change impacts communities and human habitats worldwide and in locally different ways. The adaptation to this changing world is extraordinarily challenging. For example, urban planning in progressively heat-stricken areas should incorporate building surfaces that reflect radiation, allow cooling wind to flow freely through neighborhoods, and place plants in areas where the provided shade is needed most. To address such needs, we are developing the required digital modeling and simulation capabilities, combining geometric modeling and computational architecture, as well as physics-based modeling and numerical simulation. The need for these capabilities becomes similarly evident if we consider farming regions or forest areas. On a larger scale, these areas are interconnected, and changes within each area can easily cause effects beyond its direct environment. In this context, modeling and simulation of weather phenomena is at the core of our work, considering detailed representations of the underlying geometric structures at the level of individual objects, such as buildings or trees. Such high-resolution data are of fundamental importance in order to adapt to the associated challenges of a changing environment and to support a climate-resilient community. Furthermore, the data obtained from the modeling and simulation of these complex environments could serve as synthetic training data, leveraging machine learning capabilities for smart cities. This avenue of research is supporting the development of synergy effects for the giga projects here in the region, such as NEOM or the Red Sea project.
Fluid phenomena are crucial to many areas of science and engineering, from climate science and meteorology to geophysics and the design of efficient machinery. The analysis of flow features requires accurate measurement, as well as simulation methods and custom visualization techniques. In our research, we tackle three major aspects: imaging, simulation, and feature-aware visualization. We focus on novel methods for complex fluid phenomena and visualize flow such that features are depicted accurately and in a way that supports human insight. We enable new feature-centric visualizations. For example, following a hurricane across the Earth for visual analysis of its intrinsic features. We do this by explicitly modeling a reference frame or observer, because computational detection and visualization of flow features are always observer-relative. Novel integral methods for fluid simulation give more accurate results over a range of different scales, from magnetic fluids to large-scale ocean simulations. Our mesh-free methods allow novel insight into materials, such as the labyrinth pattern generated by a magnetic fluid shown here. While for the ocean, Accurate particle methods are combined with large triangle meshes. Rainbow particle image velocimetry measures fluid flow with a simplified setup that achieves enhanced depth resolution by combining new optical design with custom reconstruction algorithms.
At the VCC, we also focus on developing visual computing and machine learning techniques that enable more accurate, robust, and efficient perception for controlling autonomous vehicles, either on the ground, like in self-driving cars, or in the air, like in UAVs. The grand challenge of this research is to develop visual intelligence in fully autonomous vehicles that can navigate safely and successfully in a variety of scenarios and environments. A core problem that we address here is sim-to-real transfer, which is the problem of learning to do a high-level task in simulation, for example by using computer game engines, and then transferring this knowledge to the real world. Learning from simulation offers a rich and practically infinite source of training data. However, there's a domain gap between simulation and the real world, and sim-to-real transfer aims to address this gap, so minimal training on real-world data is needed. In this example, you see that we're able to train a self-driving car policy in the Carla simulator and transfer it to an RC car that can navigate autonomously on real streets, both at KAUST and Munich, Germany, at the site of our collaborator Intel Labs. One interesting thing is that we never trained the policy on simulated snowy environments, and yet it was still able to generalize to this unseen setup. Research in this theme does not only apply to self-driving cars, but to aerial vehicles like UAVs. Here we see another sim-to-real transfer example where we teach a UAV controller to track and follow a target object on the ground in simulation and then transfer the tracking knowledge to a real UAV and demo it here at KAUST.
Look at the world around you and imagine how large the visual vocabulary of objects we experience, and guess how many. According to Nature, it is estimated that there exist around 8.7 million living species on our planet, and we're typically interested in identifying and understanding their behavior and activities. Some of these species will become even extinct before they can be studied. Realizing how AI can augment our skills to accelerate research and improve our lives, and that there is no good AI without good data, we contribute to building high-quality datasets and benchmarks, which include ActivityNet of 2015, which is a large-scale video benchmark for daily human activity understanding. It has become a community standard in activity localization in long-term videos. The Ego4D of 2021 is a massive-scale egocentric dataset and benchmark suite collected across 74 locations in 9 countries. It enables studying various human-like intelligence skills, like where you forgot your keys and whether you already added a salt or vinegar while cooking. The Artemis dataset of 2021 introduced a step towards enabling machines to comprehend emotions better and increase social acceptance of AI, decreasing the gap between human and machine emotional intelligence. It has more than 450,000 emotion attributions and explanations on more than 80,000 artworks, like "It's a painting of a bird that gives me hope." We focus on artworks since there is typically an intention from the artist to construct an emotional experience while producing this visual art. And finally, the long-tail visual relationship recognition of 2021, which is a benchmark that enables studying visual relationship between objects in a long-tail setting, where a few head classes have many training examples, and the remaining many tail classes has only few training examples each.
Machine learning in general, and deep learning in particular, plays an important role in many recent advances in visual computing. In the team I lead, we focus on the development of new optimization algorithms for training machine learning and federated learning models, and on developing the underlying theory. We aim to bridge the gap between theory and practice. In several of our projects, we're inspired by the remarkable but poorly understood phenomena observed by practitioners. For example, In a recent NeurIPS paper, Random Reshuffling Simple Analysis with Fast Improvements, we looked at the common practice of using randomly shuffled data when training machine learning models. This practice is the default in all modern deep learning systems since it robustly outperforms other approaches. We provide a theoretical explanation for this phenomenon using a new mathematical analysis which explains the effect random reshuffling has on the dynamics of SGD, or stochastic gradient descent, which is the key method used to train machine learning models. There were only a handful of works attempting to analyze SGD with random reshuffling, since this problem is notoriously hard. Our work provides the simplest and most insightful analysis and the best theoretical results. In most other projects we work on, we find that a redesign of existing algorithms is needed to achieve further progress. For example, in another recent paper, also published in NeurIPS, entitled EF21, a new, simpler, theoretical better and practically faster error feedback, we looked at the problem of training machine learning models in a distributed environment. A key bottleneck of distributed training is the cost of communication. One of the most famous techniques for reducing this cost is a combination of greedy communication compression and error feedback, which was first proposed in 2014 by Saide and co-authors. Despite enormous effort by the community, this technique is poorly understood. In our work, we redesigned the error feedback technique and proved the first complexity rates that match the rates of methods that do not rely on communication compression. We believe this is a breakthrough in our theoretical understanding of error feedback and communication efficiency.
The VCC invested its research resources to create solutions for the most demanding industrial sector in Saudi Arabia. We offer via service through industrially funded research projects to several local and global companies. Our researcher has been granted several patents, which has been turned into commercial product, either through licensing or creation of startups companies. One of the VCC startups is FalconVis, which provide digital twin solution through multiple asset digitization technology. During last years, FalconVis has worked on the largest mega project in Saudi Arabia and region. While developing technology further, FalconVis also trained and empower the next generation of young Saudi talents. We believe VCC research and startup company will have a powerful impact on a changing Saudi industry practice and encourage companies to source technology made in Saudi, providing further funds for local research and development.
KAUST provides an excellent environment for research. VCC research is supported by various core labs. The KAUST Supercomputing Laboratory provides access to supercomputing and a GPU cluster. The Visualization Core Lab maintains visualization facilities and VR equipment. To realize our designs in practice, our faculty can use fabrication devices such as CNC machining, 3D printing, and nano fabrication. Computational imaging is supported through devices for industrial tomography, microscopy, or cryo-EM. Now, let me show you around at our center. The Visual Computing Center is located in one of 5 research buildings that houses faculty from computer science, mathematics, and electrical engineering. The research buildings are connected by a major walkway, the spine. Along the spine are various shops selling items to support the daily research activities. Most importantly, coffee. Now, we're entering the building on the 2nd floor, where the VCC is located. We are flying around to take a look at the arrangement of offices and cubicles where staff, students, postdocs, research scientists, and faculty work. The posters on the hallway highlight successful research projects from the past. Several meeting rooms can be used for group meetings, lectures, or project discussions. Our faculty teach a wide range of courses in visual computing. Due to the excellent professor-student ratio at KAUST, some specialized courses can even be taught in faculty offices. Our research can also directly be applied to such a video stream, for instance, for activity recognition. Or depth estimation. One part of the VCC is dedicated to the Computational Imaging Lab, which allows for optical setups and the development of combined optical and computational imaging systems. VCC facilities are directly adjacent to facilities of the Visualization Core Lab. For example, the Next Cave. And the large display wall shown here. We would like to highlight the VCC startup company FalconViz that took the drone footage for this video. This concludes our presentation of the VCC. Our members thank you for stopping by and visiting with us. We hope to welcome you in person in the future.